We already looked briefly at strain gauges and how they behave. We're going to look a little more closely this time in figuring out how to turn strain gauges into load cells so that we can measure forces and moments. Applications? Well, stress is hard to measure, but you can infer it from strain. And you'll get that in some of your other courses in solids and materials. And the strain will tell you how mechanical systems are deforming under stress. And we're particularly interested in being able to measure forces. And if we can measure a force applied by how much our beam bends, then that would be advantageous to us as a force measurement device. And this approach is widely used in load cells to measure forces where we really want to know what's going on in dynamic systems. So we saw before that if we stretch a beam, it'll get longer, it'll get narrower by Poisson's ratio, and the strain is the fractional elongation. So we're measuring the change in length per unit length of the material that we're interested in. And in solid mechanics, you'll find that there's biaxial stress states or triaxial stress states, and it can be difficult to resolve an individual strain direction. So we're going to try and make our gauges sensitive to only one direction so we can separate the stresses into their various principal directions. We saw before that the electrical resistance of a bar of metal goes up depending on how you stretch it. If it gets longer, it goes up. If you make the transverse area smaller, the resistance goes up. And if you change the state of the bar so that its resistivity changes, that will also cause the resistance to go up. So when we apply a load to that bar, the strain increases the length and decreases the diameter and distorts the crystal structure. So the resistance goes up. And how big is that change in resistance? Well, there's a change in resistance due to the change in length, and we've got some derivative dr dl for the change in length. We've got a change in resistance due to the change in cross-sectional area, and that's going to also result in a change in resistance. And then this is the change in resistance due to the change in the resistivity. So those are the three factors expressed mathematically. And if we look at the change in length and the resistivity, then we're going to see an increase in the total resistance dependent on the resistivity divided by the cross-sectional area. So this dr/dl, if this is the resistance, then taking a derivative with respect to L will just give us the resistivity divided by the cross-sectional area. Here, if we're interested in the cross-sectional area, it's an inverse, so we'll wind up with cross-sectional area squared down there. And finally, if we take the derivative with respect to the resistivity, we'll get this coefficient here. So it's fairly straightforward to look at the three effects, and if we combine them, we get this equation from Figliola and Beasley. And in fact, it can be simplified if we know what Poisson's ratio is that relates the cross-sectional area change to the length change. Now, we don't need to worry too much about that if the resistivity is linear and we choose our materials carefully. We're still going to see that this change in resistance divided by the resistance is proportional to the change in length divided by the length on some basis that depends on the Poisson's ratio of the materials and the resistivity of the materials. But the bottom line, change in resistance is going to be proportional to change in length, which is proportional to the strain. And if we can measure small changes in the resistance, then we are actually able to infer those small changes in length. We saw this foil strain gauge example before. Many thin little resistive elements that are going to be sensitive to stretching in the vertical direction here. And because these things are thick, not so sensitive to stretching in the horizontal direction. So the resistance of this element will change. And if we look at actually going out to buy some of these, this is what they'll look like. This is a plastic carrier with some thin film conductor etched onto that plastic carrier. And it's got some little lines here to help you align it with your workpiece. And as we stretch this in a vertical direction, the resistance is going to change. These pads here are places where we can solder our wires. Now, for high quality strain gauges, we're looking at somewhere around $200 for a package of 10. And we can get them in a whole variety of different configurations for making our measurements. You can find a whole lot more information if you go to the Omega website. Now, when we go to apply these, we might be able to get some considerably cheaper strain gauges if we go off to eBay. For example, $4.44 for 5 pieces. These are not the precision strain gauges that we might be getting from Omega. Now, when we get a gauge, we're going to need to know how this particular gauge changes with changes in length. And that's going to come down to the gauge factor, and that's going to be provided by the manufacturer. And that gauge factor is actually this collection of stuff in here. 1 plus twice the Poisson's ratio plus this resistivity effect. But where we're going to get that information, we're going to get it off the package that we get from the manufacturer. And it's always going to be a value about 2. So that the resistance change is going to be about twice as big as the change in length. We can get strain gauge configurations in a variety of layouts so that they're all mapped onto the same device, so that we can mount a single device and have multiple strain gauges all aligned with each other. This one, as you can imagine, would be for measuring biaxial stress in perpendicular directions to each other. Here's a long, narrow one to fit onto your workpiece. These ones here, they're all associated with getting you 3 different orientations at different angles to each other. Again, to assess the stress state in the material of interest. But in this course, we're going to concentrate on those that are shaped more or less like this and sensitive in only one direction. Here's an example of the whole variety of configurations you can get from Omega. These are all on plastic substrates with the thin film conductor laid down on the plastic substrate. Some overlapping so that we can zero right in on a particular area. Some spread out so that we've got a little better orientation to be able to see what's going on a larger specimen. And the foil that's on these plastic substrates is typically very thin, in this case about 5 microns thick or 6 microns thick. The carrier will be a different kind of plastic depending on what sort of carrier it is, and it'll also be not very thick, about 15 or 20 micrometers thick. So if we're mounting this on any kind of substantial measurement device, the elasticity or the stiffness of the gauge is going to be really small compared to what it's mounted on. Nominal resistances, typically in the range of 100, 120, or up to some larger values, but still typically under 1,000 ohms. Tolerances, depending on the quality of the gauge, you'll have differing tolerances and differing variations on the gauge factor, because the gauge factor is going to vary from manufacturing run to manufacturing run based on the actual manufacturing tolerances and the alloys that are used. You'll also find some more specifications about what you can use these devices for, what temperatures they'll work at, and the range that you can work in, the temperature characteristics, so how much you're going to see variations in measurement if you mount them on different elements, how big you're going to see a variation if they're uncompensated, and if you do some tolerance for temperature compensation, you can get down to very small temperature variations. So maximum strain, this is a key one. These strain gauges will go up to 3 or even 5%, but usually we're looking for much smaller strains if we're making measurements on metals. The resistance change, as we saw before, if we're looking at making a measurement on a metal that has characteristics, say, similar to mild steel, we're usually looking at about 0.1% change in length, which translates to about 0.2% change in the strain gauge resistance. A voltage divider, like we used for our cadmium sulfide photocell or for a thermistor, would work great for those ones because there's a large change in resistance here. But when we go to use a strain gauge, the voltage divider is way too coarse. We're seeing very small changes in voltage. So we need to use a bridge circuit. And that Wheatstone bridge allows us to get, we're still seeing very small changes in these two voltages, but the difference in the change between these two voltages will tell us how much one of these resistances or the collection of resistances altogether have changed. And by doing that, we can isolate the small resistance changes from the larger voltages that we're trying to measure, and measure fairly accurately on a low voltage scale. And we did some assignments on this earlier. Now, if we've got a Wheatstone bridge like this, then initially, if these resistances aren't exactly the same, then we'll start off with a little bit of difference between these voltages. It won't start off at 0. We can add some additional resistors in here that will allow us to balance that bridge so that we can start off at 0. That makes our system more complicated, and it adds a manual step, all just so that we can make sure that VA and VB are equal to each other, so that the difference is 0 when we start our measurements. We could just as easily go and set it up so that we know what the difference is when we start our measurements, and then we can track, instead of tracking the absolute value of this measured voltage, we can track how much it changes. So in our course this time, we're going to use no balancing circuitry at all. We're going to just count on each of these resistances to be about the same, so that this will be close to 0. And when we start measuring, we're going to start off figuring out what that value is at 0, and we'll track the change in that value. Now, depending on how we set up our gauges, we can make them sensitive or insensitive to different things. So suppose we have a beam that's subject to force, tension force going off in each direction, and also to bending. If we put gauges on top and on the bottom, so we'll call this resistance 1 and this resistance 4 for the strain gauges, and if we put them into a bridge like this, with gauge 1 here and gauge 4 down there, then both gauges will be stretched by the force, and we'll get a measure here that's sensitive to that change in resistance. This one, if we stretch it, this resistance will go up, and this voltage will go up. If this one down here, we stretch it, this resistance will go up, this voltage will go down, and the measured voltage across the bridge will change due to changes in both of those resistances. On the other hand, if we apply a moment to it, this one will change positively, or actually, if we're bending this way, this one will compress, so its resistance will go down. This one will stretch, so its resistance will go up. And the changes in these two voltages here will be offsetting. So you can try that out. You've got compensation here to eliminate the moments and just focus on the force measurement. Now, in our lab, we're going to set it up the opposite way around. We're going to eliminate force effects, and we're going to concentrate on being able to measure the moments in our cantilever beam load cell.